And welcome to this demonstration video for the telemetry system that I have built over the past few weeks. As I'm sure you remember, in the previous demonstration video, I walked you through the entire process of how everything happens from the client to MongoDB Atlas charts. This time, I won't be focusing so much on everything, as much of it remains the same. Clients still use the same SDK to contact an API application on AWS, at which point the data is sent to the cloud, and then where MongoDB gets it, and then you can use their inbuilt tool to see the chart. However, this time I'd like to focus a little bit more on the testing that I did and how I arrived at this architecture that you see now. Speaking of which, let me explain to you what this new architecture is. So if you have a client running on an IoT device, it collects some sensor data. Let's say it's temperature, humidity, and AQI as you see here. It'll send it using the SDK. The SDK will append the time and the client ID, at which point it'll be sent to the Fast API application. Here, the Fast API application verifies that it's in the correct format and adds a unique UUID. Then, the Fast API application sends it into an SQS queue and returns to the client that success, it worked. The Fast API application puts things into the SQS queue very fast. It can handle about 2200 requests per second. And once it's there, a listener process will slowly look through the queue, pull out data, and send it to MongoDB. At which point you can visualize it using their tool, and you can extrapolate the data and do whatever you want with it. But why did I change the architecture? How did I come to this? Let me show you some of the testing that we did to arrive at this architecture. Let's start with the very first stress test that we did. This is on the original architecture, and over here we can see many different details. Firstly, this orange line you can see here is the failures per second. The green line is the requests per second. Keep in mind that the requests per second includes requests which have failed. It's not only the successful requests. Here we can see the 95th percentile response times and the 50th percentile response times. And down here we can see the number of users, which for this test was capped at 100, increasing at a pace of 10 users every second. We can see that the total requests per second with this original architecture does not exceed 50 at any time. It tops out at about 45. Additionally, the average response time goes up to 2 seconds, and the 95th percentile response time goes up to 4 seconds, which isn't great. However, before we decided to change the architecture, we ran a few more tests. The first of which was a simple get call stress test. In this stress test, we simply called the get function. This gave us a better idea of how the API would perform when doing a less complex task. Here you can see 3 different runs. As you can see, on the first run, the number of users was extremely small, limited to 10. As a result of this, the response times were extremely low, not exceeding about 100 or 200 milliseconds. Additionally, you can see that the total request per second was also not very high, not going above roughly 10. In the second run, we changed the number of users from roughly 10 to roughly 100. And here we can see the first readable results on the chart. Response times were about a second for both median and 95th percentile response times, and it got up to just over 100 requests per second. This is good news. This tells us that the API can handle more requests per second, and it's the task that it's performing that's slowing it down. And this allows us to sort of think about what the next iteration of the architecture could be. And on this last stress test, we tested with 1,000 users. And here is where you can see the API is sort of reaching its limits. We can see that the 95th percentile response time is reaching 8 seconds. Simultaneously, the total request per second is over 300, which seems great at first glance. However, there are also a substantial number of failures, just over 200. This means that the successful requests in this test and in this test were the same. This is because we know that there were just over 200 failures and the total requests were just over 300, which means the successful requests were just over 100. This also tells us that this extremely low median response time we're seeing here is only a result of the failures. Because when a failure happens, it's responding instantly with the connection refused. And because of that response time is incredibly low. However, it's still more than the response time we see here. And the 95th percentile response time, which will be among the responses which are actually succeeding, is extremely high at 8 seconds. Before we change the architecture, we ran 2 more tests. The first was a dummy test or a do-nothing test, where we simply tested a new function called do nothing, which immediately responds with success, it worked, and doesn't do anything in the middle. Again, we tested it with 1,000 users, and this test was quite promising. This showed us sort of the limit of what the API could handle if it wasn't making any calls to MongoDB. And this is quite promising, as I said earlier. Around 2,200 requests per second, as you can see here. No failures, and a response time of around 400 milliseconds. So this was very promising, and we decided to do one final test, which was, instead of just doing nothing, we added a sleep for 500 milliseconds in between receiving the response and answering it, just to give us a clue as to maybe how long the call to MongoDB was taking. In this, we saw something not so great. It was an 80 millisecond, what am I saying? The request per second reached 80, which isn't great. It's a drastic reduction from the previous test where we were getting 2,200. So this is like maybe 3 or 4% as fast and the response times were also incredibly high. 12 seconds for both the median and the 95th percentile response times. And once again, number of users was 1,000. So this gave us quite a few clues as to what the problem could be. And we changed the architecture for the first time to an asynchronous architecture. Let me show you that now. Here we have several stress tests for after changes to the architecture. So in this first one, we were using an asynchronous architecture where we were making a new background process for each separate request. Ignore this first run. I believe I had forgotten to actually start the API on AWS. In the second run here, we can see that it appears very promising at first sight. Over 300 requests per second and minimal failures. However, that's not great. There still were failures, as you can see here. And another problem, look at this response time. 6 seconds. That's quite bad. And the reason for this 95th percentile response time is that as the number of users climbed, and it was supposed to reach 100, the program crashed and stopped responding. As you can see here, we received this response long after the number of users had hit 0 and we stopped sending out requests, which was an indicator that it had crashed. As well as this, the terminal I had logged into from this laptop to the AWS system stopped responding, which indicates to me that there were too many background processes and it crashed. A similar issue happened here where it crashed after a while. However, in this test there were less users, as you can see, only about 200, and the response times were also lower, only about 2.5 seconds, and we were getting the same request per second with no failures. But you can see this graph remains quite similar. It initially spikes and then goes down, and same thing here, it initially spikes and then goes down. So this told us that this architecture probably wasn't the way to go, because under load it was crashing. So we made the next change, which was switching to an SQS queue. This first change was using a FIFO queue, and we were just putting the data into the queue and returning success. And this seems really bad at first glance. Firstly, I'd like to admit I made a mistake. I had run another test before this with only 100 users, and I forgot to save that, but that test went extremely well. It was about 220 requests per second, no failures, good response times, and 100 users, as I just said. However, when we ramped that up to 1,000 users, we ran into problems. Firstly, a FIFO queue throttles after 300 requests per second, and once that throttling started, it caused a small amount of initial failures, and then for whatever reason, those initial failures led to more failures. And you can see that here, that these lines just converge and every request becomes a failure, and a similar thing here. Additionally, response times peaked quite high. You can see this reached all the way to 30 seconds, 15 seconds, 20, 25 seconds, and it wasn't great. However, at this point we made the next change. We upgraded to a larger machine from T2 Micro to T2 xLarge. This has more cores, more RAM, and we just wanted to test that out. And it went great. Though these results that you see from the previous test weren't that good, we thought we should try it because the 100 user test went so well. And this is really promising. 300 requests per second, and on this graph what looks like no failures but was actually about 1 or 2 failures per second, and extremely low median response times, and then obviously 95th percentile response times are quite high, and about 200 users here. The reason for those 1 or 2 failures was the throttling I mentioned earlier, but for whatever reason the more powerful machine could handle that better, and the response times did not spike, and more failures were not introduced as a result of that. At this point we decided it was better to go with a standard queue, because then we wouldn't have to deal with throttling. So we switched to that, and finally we saw this. This was amazing. It was able to do 1,000 users, less than 1 second response times, and over 2,200 requests per second. This was simply amazing, and it worked great. And I'm sure you remember from the last demo, Atlas charts, MongoDB, all of that is still working the same. You can still see everything. Only difference is the SQS queue, and now it can handle many more requests per second, which is fantastic. So thank you for listening to this. Once again, I will put the code up on GitHub and then put that link in the description if you'd like to see it. This worked great, and in the future, some more ways we could improve it are batch messaging, where it receives 10 messages and then sends those to the queue. that would save some bandwidth. It would also make the request per second faster. And that's a possible next step if we decide that we need it. However, for now, the system is working great. We can see I have no complaints. And thank you for listening.